Hello everybody. We're having a bit of a bad day for recording video and we're trying something new as a result. So I apologize for changing systems on you. We'll see how it goes. Today I'd like to talk about understanding functions of several variables a little bit better. So when we're looking at functions with n inputs and one output, that's one of the simpler types of functions that we could analyze, and that we call a real valued function. One of the ways we often think about this is if the inputs are some kind of position, like a position in 2 dimensions to measure where we are in x and y coordinates, or a position in 3 dimensions to measure a position in space, we could think of this as measuring at each position some quantity, like the height of the ground at a position x comma y, or the temperature at a position inside 3-dimensional space, or many other quantities that we could think of measuring. In these kinds of cases, we may be able to draw graphs of the function. We might not. Doing so takes work, and let's talk about how we do that. So one of the main tools we have available for understanding these types of functions is what's called a level set. A level set is what we get by taking our function and setting it equal to a constant. That level set is that in the set of solutions to that equation, and it draws for us a little map of exactly where the function is at a certain value. And we could let that value vary. Every time we plug in a different value of this constant c, we get a different level set. And as those change, we get a picture of how the function is behaving. When we're in 2 dimensions, we call this kind of a topographical map. So here are some examples, and these examples represent success in me getting Mathematica working on my computer, which is a lot less exciting for anybody else other than me. So in the left-hand picture, we've got the function f of x, y is x plus y. And here, for example, we've write down the equation x plus y is equal to 0. That draws a line that starts in the upper left and moves to the lower right. That's one level set, a level curve. When the constant is equal to 1, we're drawing the graph of x plus y is equal to 1. That's this diagonal line. And as we change the different values of the constant, we get different lines, but we can see a little bit about the function from how this behaves. We can see that as the value changes, we get a sequence of uniformly spaced lines. And so there's kind of a uniform change in the function. It moves kind of step by step by step as we go from kind of the lower left to the upper right of the picture. Whereas if we move along the other diagonal, the function changes, it stays the same. Now the picture on the right has its labels screwed up. And so let me pretend that I didn't do that. So here, we've got the function f of xy is x squared plus y squared. And so we're drawing the solutions to equations like x squared plus y squared is equal to 0, or x squared plus y squared is equal to 1, or 2, or 3, or 4. And each of these is a circle, the circle of radius 0, the circle of radius 1, the circle of radius 2, or square root 2, centered at the origin. And we can see from these level curves that the function, because the function starts out with these big gaps between the level curves, and they get thinner and thinner as we go farther and farther out from the origin. All right, now the behavior of the level curves like that tells us properties of the functions. So here on the left and right, we've got 2 different kinds of functions where the level curves look pretty much the same, but in the function on the right, they're more tightly packed. And so here on the left, we've got the function x plus y, and on the right, we've got the function 2x plus 2y. The fact that the level curves are more tightly packed indicates that the function is changing more quickly. So like that is exactly what happens with topographical maps. If you look at a topographical map, you see that the curves are very tightly packed when you have rugged terrain. And that's exactly what's happening here.